Good morning. I have to say, I've never given a talk in such a spectacular environment. I think the lights flashing help a lot. Do you think that? Anyway, it's, and I really enjoy the opportunity. I sit at my desk at Harvard thinking about these weird ideas, and seldom do I get a chance to speak to an audience like this to explain it. Why? Because it's my ideas? Well, maybe. But the ideas that I'm understanding, contributed by thousands of other scientists around the world, are going to change the world. So, today's talk, yesterday I tried to describe what AI-based data science is, its philosophy, its limits, its power. And now today I'm going to explain how you solve problems with it. But I'm going to give you a warning. I don't intend you to fully understand what I'm about to say. What I'm about to say is provide you the structure of the way in which such problems are solved. And I will use that structure to explain why and how we don't know it works. And that's the main purpose, as well as to show you the crucial element in problem solving with data science is data. And so how data enters the picture and is both great and a huge challenge. But before I get going, I'm going to give you my email here. So far at the Congress, there has not been a lot of communication between you, the audience, and we, the speakers. So if you have questions that you would like answering, or maybe some topic you would like repeating, we will have a panel tomorrow to answer those questions. Not just me, but other of the main speakers will be on the panel. But in order to have a panel that responds to your questions, you've got to give us your questions. So please send an email to me at Harvard. I'm not there, I'm here. And if we get enough questions to warrant having a panel, we'll do that. Okay, moving right along. So yesterday I tried to talk about the nature, the philosophy, and the power of what I call AI-based data science. What I was trying to show you was, oh, this screen isn't on? If you could fix that. Oh, but this one is. Okay. So AI-based data science is a new paradigm. It was invented essentially in 1943. That was the first idea. And it really didn't gain power until about 1986, but it really took off about 20 years ago. So novel means it's only been around for about 20 years, and it has more power than science. It was what I tried to... Isn't that amazing? The most powerful knowledge discovery paradigm in the history of humans has been science. And now this new stuff is vastly more powerful. It'll expose to us more knowledge than we have ever seen. But some of the knowledge it'll expose to us is, pardon the expression, bullshit. Because I have this idea that science is trying to present to us hypotheses that are true or false. So it's a very certain world that science presents to us. But I think, in my experience, the world is not certain. It's very uncertain. And data science works with that uncertainty. The power of the AI-based data science is power to create solutions or predictions for something, and those, just like any tool, can be used to create or destroy. So I said yesterday it will translate every data-rich both profession, job, or task. We don't know how it exactly works. And the solutions, as I said a moment ago, are not concrete answers that science gives us. They are intuitions. And you look at the intuition and you try to follow it out, and I'll talk a little bit later about where you look to ensure that it might actually work. And like any revolution, like the Industrial Revolution and the Scientific Revolution, both of which took somewhere between 200 or 400 years to mature, the AI revolution is just beginning. And in a decade, we'll know a little more. In 50 years, we'll know even more. So I suspect it'll be about 100 years before we really fully mature it and understand it better. So I'm going to tell you today about AI-based data science. I'm going to give you this structure about the way in which the problems are solved. And part of that is to show you that you've heard of ChatGPT and you've seen that AI applications are everywhere. They're not simple to create. They used to be. When you had a relatively simple problem and you develop a single model, what they call, to develop a solution, we've passed that stage. Now we're dealing with really significant problems, domain problems, like in biology or in medicine or any other area, and it's not easy to solve those problems. So I'm going to talk about what I call the problem problem. The problem is knowing how to solve the problem. And in the process of knowing how to solve the problem, can you demonstrate that the problem you're solving is the one you intended to solve? Because the AI, the neural networks that we train and use to solve the answer, we don't know how they work. And so you can't establish that the way the problem is being solved or what it is solving is what you actually intended. So it's a little tricky. It's inscrutable in a bunch of ways, and the structure will allow me to tell you that. I'll tell you about the role of data in science. And the reason the scientific revolution and the industrial revolution took 200 to 400 years is, first of all, you've got to understand what is the paradigm shift you're going through. You've got to understand the new concept, understand the new thinking and reasoning that that concept enables, and you've got to forget what you've come from. And then having done all that reasoning, you've got to then apply it. Like in Manchester, in factories in the Industrial Revolution, they were producing wool and trains and all sorts of things. How long do you think it took for that kind of machinery and that kind of problem solving to get to China or Thailand or Vietnam? That's what the 200 years is about. And what occurred to me while sitting with you listening to the economists and the financial people, I realized that AI is a yesterday I said it's an AI revolution, and that's on the title of this talk. I actually realized it's a meta-revolution. So in problem solving, it's a revolution. It's something profoundly different than the way in which we've solved problems in the past. So that's in the domain of problem solving. However, this problem solving enables other domains to have revolutions, like the monetary revolution, or the biological revolution that's going on, or the drugs revolution. So anyway, I just thought this is a kind of a cool term. It's a meta-revolution. Do you like that? How are we doing this morning here? All right, I'm having a good time. And so to illustrate, because today's theme is about economics, I'm actually going to give you a little bit of evidence about how it's applied in economics. So now we're going to come into a slightly complicated area about how does one solve a problem at all? And this is called a problem-solving framework. So you want to solve a problem, that's the problem there, and often it's parameterized, like the size of the problem or some of the factors you happen to know that determine the nature of the problem, and you may have some insight as to what the results are to help you solve the problem. Normally, when you're solving a problem, it exists in a bigger context. And so you say you're trying to solve some problem in agriculture, and you basically know how many things happen in agriculture, but you're trying to solve a particular problem. What you do is you take the understanding that you currently have. These things never work on the slides. You take the domain knowledge you already have, and you augment it with a hypothesis about how to express the problem. That causes you to have a domain solution, which involves what you know and what you think you know. You then apply the domain solution. You get a domain solution result. By the way, that's not what you're after. It's a result within the context. So you now have to look inside the result that you got and interpret the domain problem result, which is the thing you were starting off with. Now, almost all sophisticated problems are not solved directly like this. I'll give you the Higgs boson example. You don't need to know particle physics, but I'll just use it to illustrate this. The problem you want to solve is, this is the most famous experiment in the 20th century. Does the Higgs boson exist? And the question there was, we knew there were 61 elementary particles, but how did they get their weight? Because gravity doesn't apply within an atom. So how do they have weight? And Peter Higgs in 1962 hypothesized, together with two of his colleagues, that there was a force field called the Higgs field, just like a gravitational field or an electrical field. But this force field, which they were going to call the Higgs field, gave weight to all of the elementary particles. And then, just before publishing the paper, he added a paragraph, and maybe that field is a result of another elementary particle. So anyway, you want to find out what the Higgs boson is. You already have a knowledge of what's called the standard model of particle physics. You hypothesize what the answer is, so you extend the standard model of particle physics with your hypothesized behavior and weight of the Higgs boson, and then you run the experiment in the Large Hadron Collider in Geneva, and you get out a lot of information, and that's where I worked in the experiment. I was on the experiment in Geneva, and we looked at all the data, and we got the answer out. Yep, it does exist. So we can't play within the atom. It's too small. So we develop an analytical model. So corresponding to the standard model of particle physics, we have a simulation model. So it's a standard model of particle physics simulation model. So anyway, you understand that most problems are solved analytically before you go back to the actual phenomenon you're looking at. And that's because, and so this is the way that it's solved in, let's say, in particle physics or biology or anything. Number one, what is the problem you're going to solve? You've got to define what it is you're going to solve. You have to have a lot of knowledge about that. Number two, you translate it into the analytical model, so you're designing the solution you're looking for. You then apply that solution that you have designed, and these are all done in simulations for the Large Hadron Collider. And then you get an analytical result, which produces you get an analytical solution result, which gives you an analytical problem result, and the trick now is to map it back to the other side. So this is only the analytical portion. Now we go back to the experiment itself. And you first of all define the experiment, done that already. Now we have to set up the experiment. Setting up the experiment for the Higgs boson took roughly 40 years. Building the Large Hadron Collider started in the mid-'80s and didn't conclude until they made their first runs in the early 1990s. And the actual Large Hadron Collider experiments didn't start until about 1998, because the projects were only approved in 1997. You then apply it. Now notice this is all on the phenomenon side. So you then apply it. That is, you run the Large Hadron Collider for 2 years in this case, and then you get the result out. So you don't need to know all those details, but I was just trying to demonstrate that the most sophisticated scientific experiments are done this way, and even in engineering they're done this way. So there are two main processes, the discovery itself, and that is defining, designing, applying the experiments, and getting the result. And then the most important, well, a very important part now is how do you interpret that result? And I'm just showing you this because when we get to data science, there is no interpretation. Oh, the interpretation in science is entirely dependent on the way in which you've done the design and executed the solution. There's no such trick in data science. So most problem solving involves the domain problem, which is on the right, and the analytical problem, which is on the left. So the most analysis, like in building a bridge, is the bridge. And the analytical side are all the models you use to design the bridge and structure the bridge and test the bridge. And you do all that on data, not on the phenomenon. What's different between most problem solving and science in particular versus data science is all science is analyzed on the phenomenon itself with intuition from the analytical model. And I'm sorry to go on about this, but this is a fundamental shift. The way in which data science is used, it is never done on the phenomenon. Never. It doesn't work that way. It works on data that represents the phenomenon, and the analysis is done on the data. So this is pretty simple, but it's fundamental. Most analysis prior to data science was done on the phenomenon aided by analysis. And in data science, it's all in the analytical world. So let me show you how the problem is solved in data science. What's really striking about solutions in data science compared to science is, in science, you generally know the context you're trying to solve in, and what you're trying to get is a solution to help you solve that problem, which gives you deep insight into what it is you're trying to solve. Can you imagine solving a problem when you don't understand the context, you don't characterize it, and you never, almost never, have a solution on the domain side? For example, in protein folding, we know that proteins fold in a particular way, and the three-dimensional structure of a protein helps to define its function. And we also have been able to produce those protein foldings with about 5 or 10 people over 5 to 10 years. And it's all done with complicated computing, which is more or less a simulation. In most data science applications at scale, we don't know what the domain solution is, and actually we don't care. All we want is the answer. So let's see what happens. First, you start, as you do anywhere, you define the problem. Secondly, you translate it into data science. That's where the problem starts. Which neural network are you going to start with? There are hundreds of them. But you've got to choose the neural network that does the generic type of analysis that you want doing, and you can only describe that generic thing. Let's say classification. It's going to look at images, and pizzas are different than teapots, are different than chairs. So that's a classification algorithm. What happens is you give it training data to train the model, and we have no idea what it learns. But so I'll give you some examples of what we do know what it learns, but we don't know how it learns. So let's say we give it an encyclopedia in English. In analyzing that encyclopedia, not only does it internalize somehow the knowledge in the encyclopedia, it also internalizes the structure of the English language and the semantics. All of it, I don't know. But when I ask ChatGPT, it seems to understand. Then we give it another the same encyclopedia, but in French. And not only does, actually no, sorry, I'll make it more fun than that. So let's say we give it, let's say 1,000 books in French. It learns the structure of the French language. And when you ask it a question in French pertaining to information that it gained from the English encyclopedia, it answers. Somehow it's translating from English to French because it knows the structure of both languages. Do you believe this? I mean, it's hard for me to believe. I've spent my career doing this stuff. So where are we now? Oh, yeah. So then you get the trained model, and you apply it to data, inference data. You get a result, and you map it back, and we're done. In the science case, after you go through the analytical part where you try to understand how to solve the problem, you now go back to the phenomenon side and solve the problem. Here, we're done. As I said before, the discovery part is difficult enough. I call that the problem. But the interpretation part is in red because it doesn't exist. In science, in engineering, and most other problem-solving environments, the way in which you solve the problem is the method by which you prove that the solution you came up with is correct. And in AI, we have no such chance. So now let me, you don't have to remember all that. Like, I'm not going to come up with you at coffee and say, how do you do this? I'm giving you this to illustrate to you some of the fundamental challenges in machine learning. And the first is we have no idea how a training methodology, or I shouldn't say that, how the neural network is trained using a training methodology. And there are many, many, many training methodologies. We don't know what it has learned in the training so that it produces a model. We don't know how to, remember that thing I said, when you solve a problem in the analytical space, you want to make sure that it corresponds to the problem you thought you were solving in the domain space? We have no idea how to do that because we don't know how the trained model works. So that's a sort of a useless task because we don't actually know the domain solution. We don't have one around. And then we don't know how the trained model discovered what it discovered. That's that bubble there. And we also don't know how to interpret it. When I say we don't know, and yet you've seen all these systems work, what I mean is we have no theory to demonstrate or to prove that we know what's going on. But there's a tremendous amount of engineering techniques that allow us to do this stuff, and we sort of think we're right, but these solutions can also fail. Now I'm going to tell you the importance of data. And if the knowledge you're trying to discover is not in the data you're using, then you're not going to get an answer. So data is absolutely crucial. So when we want to train an image recognition technique to recognize pizzas, you've got to give it a training data set that fully represents all of the features that you believe all pizzas in the world have and ever will have, so that the model can be trained to say, oh, I got it, I know what the pattern is. And then you need, when you go to give it an image and say, is this a pizza or a chair, you've got to make sure that that image has within it what you know to be a pizza. Now, that's pretty easy talking about pizzas, but when you're talking about financial banking systems, you need to understand all of the entities, financial entities, and all of the transaction, all the semantics that were talked about in the previous 3 sessions. You've got to understand that enough to give it data to train and then to use it in practice, and that's tricky stuff. So what we don't understand is how or what it learns in training, or how or what it learns in discovery, or how to interpret a result. So, and this takes a lot of engineering and empirical experience. Yesterday I told you about AlphaFold, which is one of the most remarkable solutions. And we know that it is as precise as the angstrom measure of the 3-dimensional structures in a proton. Not a proton, protein folding, and a protein. So we know it's as accurate. But because it's being used for drug design, they run it at least 4 times. And they do a lot of analysis to ensure that they've got it right. And then you step out of data science and you use biology and structural biology and other mechanisms to demonstrate that what you have found is actually true in the real world. So we have no way of proving properties of it, and that has to be done with engineering. How do we address inscrutability? Within data science, there's no theory to tell us is it right or wrong. There's a tremendous number of engineering tricks. And hallucinations, I mentioned hallucinations yesterday. Hallucinations are when a model that is produced, or an answer that is produced from machine learning is not factual, or it's fabricated information, or it's just plain weird, or it doesn't correspond to your question at all. And that happens even amongst the most sophisticated and refined models, because it's the very nature of data science to generalize. Remember I said it sees 10,000 pizzas, and it can look at 1 million pizzas that it's never seen and say they're pizzas. That's called generalization. And that happens in every domain. So you don't want to turn that off. If you turn that off, you've lost all the power of modeling that you could have had. And yesterday we heard a lot from ethicists, from a philosopher, 2 philosophers, on how this stuff should be governed. And I'll show you in a slide in a moment the number of such things that are going on. But be clear that this has nothing to do with AI. It has to do with morals, beliefs, social norms, and governmental actions. So in Europe alone, I read a report, a woman who was on the European Council, she now works at Stanford on AI, because she helped set up the guidelines in Europe on AI. And she wrote a paper recounting about roughly 400 guidelines by governments, countries, and local bureaus on how to manage AI. That's a good thing, right? Everybody's concerned. It's not a good thing. Meaning to say that if 2 companies are building a product, they both have different guidelines. So the United Nations in 2018 set up a resolution on AI. So we also heard from philosophers yesterday that China has different morals and ethics than North America. North America, he claimed, was market-based, and so their guidelines would be have to satisfy market-based. And in China, it's more restrictive, so they wouldn't want ChatGPT running, would they? Because you could ask it a question about politics. And so it doesn't run in China. So I'm just trying to say that there are amazing things everywhere. I won't go into it all. The EU Act that was, the AI Act for the European Union passed a couple of months ago. That's the first legislation in the world that's happened on it. Is it early? It's very early. Will it be refined? It will have to be. The White House in 2018 put out an executive order from the president, which meant that the executive order applies to all government agencies. And it was saying, when you use AI, it has to be in support of the people and can't be harmful, blah, blah, blah. 2 weeks ago, it put out a new declaration. Oh, maybe I should state the obvious. Every government agency has been mandated to apply AI as much as they can to improve what they do. So it's widely used in the US government, or let's say it's being experimented with. So the executive order that came out 2 weeks ago is every government agency in the United States has to prove to the White House that they are using it and that it complies with the 2018 order. So there's a whole lot more. And the one that interested me so much was IBM made an agreement with the Pope. Yeah, you heard it right, the Pope. And the Pope and IBM put out an edict about how AI should be treated. Step 1. Step 2. The Abrahamic agreement was announced. The Jewish religion, the Islamic religion, and the Catholic religion put out a joint set of guidelines. Have you ever heard of leading religions in the world pronouncing about technology? So you can see that the world's very concerned. So we're in a paradigm shift. We're going from the way we used to think to the way we need to think should we want to take advantage of AI. So science is giving us very definitive, concrete, provable answers to complex problems, but it's done at human scale. AI, on the other hand, it produces insights beyond scales that humans could ever think of, which means you can solve small-scale problems, but massive-scale problems you've never thought about. And I remember I said, or at least I said yesterday, AI doesn't know what a pizza is. It knows that this thing that has pepperoni on it is associated with the text pizza, so it doesn't know human concepts. What does that mean? That also means that AI can discover stuff that we haven't labeled with anything yet, concepts. And it will see it because it's been trained on the entire internet and corpuses of millions of books. It knows pretty much everything we know, or mankind has known to date. And it may be able to find stuff that we haven't thought about before. So data science thinking. So remember I said you've got to understand what the topic is. You've got to be able to know how to reason with it, and then you've got to apply it. So what you need to apply is domain thinking. This is no shortcut to not understanding biology. You don't turn to AI and say, make me a new drug. You've got to understand deeply biology, what the nature of the problem is you want to solve, and what data, I'll come to the data in a moment. And you need to know the nature of what it is you're looking for, and you want the AI to look for in the data. Data thinking is much harder. You've got to get enough data that is representative of the features of the phenomenon you're analyzing. Sorry for all these crazy words, but I have to be precise about it. You're looking at a phenomenon, and it may have an infinite... Pizzas. There is an infinite space of pizzas. All the pizzas that will have ever been made and all the pizzas that will ever be made. It also applies to molecules. And we have hundreds of millions of molecules, and we only know about 200 million of them. So, and there's many, many more, which is why there's a possibility for all kinds of interesting drugs. So you've got to know the phenomenon you're looking for, and you've got to know the features that you're looking to analyze. How toxic is this molecule? Not only do you need to know the features you're going to analyze, you need to know the causal features. That is, it's toxic because of these other features of the molecule. So you've got to understand all of this stuff before you even start doing data science on it. So data thinking is really difficult. Computational thinking. I made this comment yesterday, and I may have made it today. At the beginning of all this stuff in the 2000s, 1986 through about 2010, most of the AI models were on simple things, and they were single models. A single neural network was typically powerful enough to recognize pictures, recognize voice, all of that stuff. Not anymore. We're analyzing very complex domains, very complex phenomena, and you need to engage in computational thinking. So AlphaFold, this amazing protein folding solution, has 32 models in it, and it was built with engineers, data scientists, biologists, and I think there's about 6 other disciplines that worked in order to solve the problem. And they solved problems in their own domain, step 1. Step 2, how do you combine the different models? Does this model go first and then this one use the result? So those are called ensembles. And there are many, part of the trick of all this is knowing how to, is the problem. How many models do we need, and how do we combine those models? By the way, for every single model, you've got to do that data thinking. Every model has to be trained, and every model has to be given data when you get to the analytics part. So my current focus in research, I spent my whole life, my whole career, I guess, dealing with data. It seems kind of nerdy, right? But all of a sudden, data is vastly more important. So since the beginning of time, so writing with script of some form goes back to 34 BC. And until about 19th century, data, which is something written, either a number or text or something like that, they were simply objects that were written and read manually. And then the Gutenberg Bible came along, and so we had the Gutenberg press. So there was a little automation in printing. So it was modestly automated a while ago. In the 20th century, most data now is automated in terms of recording and searching. So you can search a database and find every transaction that had certain properties. So that's the extent of reasoning that was done up until the 21st century. So data then became strategic because enterprises were characterizing themselves in data. And so if they wanted to strategically figure out their current value and where they should go, they did it in a database. They didn't sit at a desk and try to figure it out. They did it in data. In the 21st century, we have already got all data automated, and that's what artificial intelligence comes in. Artificial means the reasoning, the intelligence is in the machine. So now we have automated, we're at the beginning of a revolution in which we are automating knowledge. So the way I characterize it, and I'll hopefully get it better later, is data has become phenomenological. Back in the old days, it were objects that you could read and write. But now, we are using data to understand aspects of reality and our imagination that we never could have done until about 2010. Amazing, to me. A really brilliant and innovative Israeli philosopher wrote a book, Homo Deus. It was part of a series, absolutely wonderful reads. The final chapter of Homo Deus, and the premise of Homo Deus was man has proceeded from a life dominated by the gods. Everybody had different gods, but they thought the power came from the gods, and they matured through time. And his final chapter is, I hope the hell it's not data is the religion of everybody or automation. And he called it the data religion. And he characterized human history as, from the beginning of time, it was deocentric. Everything comes from God. In the 18th century, humanism came along, and everything, the religion of the world became human-centric. In the 21st century, data science came along, and he hypothesizes, he hopes it's not the religion. And the example he is if you're a 15-year-old girl or guy, and you've just had a pizza, surely you want to take a picture of it and put it on your phone. And as long as it's on your phone, you might as well put it on a social network. And this simple expression of a person's life has become extremely deleterious to human life. Social networks. I put that up there, by the way, to show you that data is important, and it also threatens our very civilization. So this day is about economics, so I was going to illustrate how AI is being used in both economics and finance. In 2014, a really brilliant and controversial economist, Thomas Piketty, has an institute in Paris. And so, remember I said data is tricky? So I'll give you an example of how tricky it is. And he did something that nobody thought was ever going to be possible. Oh, by the way, he proved a simple point. The rich get richer and the poor stay poor. That's the principle he proved. Everybody knows that. But he did it the following way. By the way, he has an institute where he uses data science to evaluate economic principles. And I believe he calls his institute in French something like equity, economic equity. So he's very much in favor of an equitable world, and that economics should be a tool to achieve that equity. So for a decade, this is when he was getting his techniques down, he got 100 years of economic data from 100 countries. And you probably know that every country changes the economic data it keeps each year to improve. Like the Bureau of Labor Statistics, they used to keep certain statistics in 1952, and then by 1962 they were completely different, and nowadays they're complete. So he managed to get data from 100 countries over 100 years, and you can imagine it's all heterogeneous, but it's economic. And he used it to prove that income from investments will always outpace income from labor. That was the simple principle he wanted to prove. And so you'd say, well, how do you know that's true? I mean, he looked at the numbers and he got the numbers out. The answer about whether anything is true in science or economics or math or biology is not biology, math, economics, and physics. It's people. You publish a paper to a journal or a conference, and the reviewers for that conference either reject or accept your paper, and that means it's true. So a scientific experiment can be absolutely true, and if the paper's rejected, the concept never goes out to the world as a proven concept. So I'm giving you that evidence because everybody said, oh, Piketty's full of, he can't possibly get that information. So other economists did the same analysis, and they proved it to a much higher level of accuracy. So it's been confirmed multiple times over to a much higher level of accuracy. Now, on AI used in investing, D.E. Shaw, as an MIT graduate, he created an investment company using statistics predominantly, and we think, we don't know, he's never published it, that we think he used AI in the late 1990s to invest. He became enormously successful. And what happens when an investing company is successful? All the other investment companies follow what they do. So that by 2018, 50% of all hedge fund-based investments were done exclusively using AI. But be careful. AI, first of all such investments are regulated, and you couldn't let AI, some non-human, make those things because they couldn't be held responsible. But it's not responsible for AI to select an investment and make the investment for you. So AI is exclusively used to gain insights, as I had said earlier, and it's now widespread across. So all you need to do is do a search on the web for books on data science in the economy, data science in banking, data science in finance. You'll find thousands of books. And so what I'm going to tell you now is an interesting story about baseball. Has anybody seen the movie Moneyball? A few. Good. Well, baseball is this game in America. You guys are kind of quiet. In 2002, there was a team, the Oakland A's, I think it was the Oakland A's, and they were a bad team. Oh, United States, there's a sort of an East Coast and a West Coast, East Coast and West Coast league, and the winners of those leagues go on to play the World Series. How can you have a World Series when only one country's involved? Anyway, so the Oakland A's were on the West Coast, And their general manager decided to follow what somebody had said would be a useful thing, to use data in analyzing hiring and firing players. And so this guy, the general manager, I'll give you just one example of what he did. They had Oakland A's, as bad a team as they were, they had the best hitter in the league. He fired him because the guy had a big salary, and he hired 4 other guys with that salary. And it wasn't the number of players. And so let me go through it. He questioned the basic assumptions that had been used in baseball, and flamboyant good hitters bring in the crowd, but they don't win games. And what this guy wanted to do was win the pennant. And so this guy, he was a hero. He wasn't a team player. He didn't encourage team playing, and so he didn't help them win games. They got people to buy tickets to the game. So he questioned the basic assumptions. Why am I telling you this? When you're going to use data science to solve problems, you've got to think about what it is you're trying to solve. So this is the problem, trying to determine what it is you're trying to solve. So then you have to, once you've given up the old metrics, or those that you think don't help you, you now have to figure out what metrics you do. So he had to figure out what characteristics of the team enabled the team to win every game, or to win games. Then value over cost. So obviously they had a high value in this big hitter, but the bigger hitter had the biggest salary, and he was inconsistent with the metrics that they should follow, and he was consistent with the old things. This is based on, you should not automatically trust data. You've got to analyze the data, and you've got to get the right data. So data doesn't provide you the answer. He's got to solve the problem. How do the Oakland A's win enough games to win the pennant? And then finally, you can imagine this general manager of the Oakland A's was extremely both unpopular on the team initially, and he was highly quoted in newspapers. But guess what? They won the pennant. That was really cool, right? But they didn't win the World Series. Why didn't they win the World Series? Because every baseball team had watched what he did. And by the time they caught on later in the year, everybody implemented what he implemented. And so when he got to the World Series, the team that he was up against was a better team anyway, but they had already applied the techniques and improved themselves. So another really interesting point to observe here is that it changed the nature of US baseball entirely. And it's all about winning games and teamwork, which I guess is okay if you want to win games, but you don't get these wonderful heavy hitters who are big heroes and run out and the audience applauses. So when you look at phenomena and you understand them better, you may actually change the phenomena themselves. So I think that AI is more realistic than science. So science solves one particular problem, has one solution. Does the Higgs boson exist or not? And there was one solution. It was figured out, and it does. We're done. You never need to look at that again. In data science, it's not a one-off. When you're analyzing, so you have a model. It's already trained. You should probably train it again and again and again through time. But let's say your model's already trained, and you apply it to some input data. That's a single instance. And data science solutions are intended to be solved repeatedly. Not only solved repeatedly, but a neural network does a particular kind of analysis. And maybe you've analyzed this data or this phenomenon according to one analysis. And it's probably worth looking at different analytical methods on the same thing because you get different insights. So AI is constantly being applied multiple times to problems, and you should probably distrust what you see. Science analyzes a problem and gives you a concrete answer. AI discovers stuff and gives you intuition into Well, you should probably think about this a bit more. Oh yeah, instances versus universal. I guess I already said that. The scope scale thing I mentioned yesterday, I went over it very fast. Science can look only at a measurable phenomenon in the real world. Data science can look at anything for which there's adequate data. And I guess I've said this many times, AI will find whatever's in the data, whether you knew it was there or not. So you may discover stuff that nobody had ever seen before, such as protein folding. Oh, my goodness. We'll have time for questions. So the data-centric revolution is here. And so the point of this lecture is how the problem is solved illustrates to you the problems and the challenges in actually formulating the right answer, and the role of data. So data is really centric to it. It has massive scope, scale, complexity. I explained some of those yesterday, and I guess I didn't go over that much today. And the takeaway message is, it's a very complex tool for analyzing very complex problems. It can also be used to solve really simple problems. I'm going to go to Nevada for a holiday. What's the best route in August, between August the 10th and August the 20th? And what should I do when I'm there? So it does complicated things. So you recall I said there's a paradigm shift, and humans got to go through this paradigm shift, and they've got to understand this complex stuff. So the world has responded. You've seen how many people have used ChatGPT and are using all these tools. And we heard earlier today, I don't know if you were here, but they recited probably 20 areas of banking in which it is already being applied. So it's being applied everywhere. And if you're not applying it in your domain, you've either proven it doesn't work, or you're going to not be competitive. So the world is moving very slowly due to the complexity, cost, and shortage of labor. It's very complex to understand and apply. And secondly, let's say you want to hire, and you need smart people in order to know how to apply it in your discipline or your institute. There are very few people around, and it costs a lot of money. Remember I told you 15,000 chips at $15,000 per chip? So it's a very expensive venture. And the guy who's in charge, the CEO of Anthropic, that just put out a data bot or a chat bot called Claude 3, he hypothesized by the trajectory his company is on, Claude 3 beats ChatGPT hands down. It's much, much better. Every week there's a new one coming out. But Claude 3 and the trajectory they're on, he predicted there will become a $1 billion model pretty soon. And that model will be more powerful than any model. He projects that model will be more powerful than anything you've ever seen. Thank you.